Hi everyone, this is chemistry term 1 week 2 grade 12 AMS. So let's get started. Which of the following are the factors that affect the magnitude of the lattice energy released from a pair of ions? Okay, so basically here all you need to do is the formula E equal K Q1 Q2 over R. So since R is in the denominator, it's inversely proportional to the energy, and the charges, the product of the charges, is directly proportional to the energy. So as you can see, that the energy is directly proportional to the charges and inversely proportional to the radius. Moving on. Thorium has 7 natural occurring isotopes. Which of the following are true about isotopes? So isotopes always have the same number of protons or atomic number, different number of neutrons, sorry, or mass number, same chemical properties, yes, and different physical properties. Okay, moving on. This is simple يعني بصراحة. If you don't know this, there's a problem. ف يعني there's an element, atomic number 90, mass number 232. You already know mass number is at the top, atomic number at the bottom. I'm not gonna explain it يعني. By now you should know. Type. What atoms of different elements have different number of subatomic particles? Subatomic particles are the neutrons, protons, and electrons. Which of the following ions have different number of all three subatomic particles? Let's see. Okay, so the ions here. So مثلا يعني they're saying here a neutron should be not equal to the proton, should be not equal to electron. Let's see what we have. Magnesium, obviously the neutrons we know, you should know, it's the top minus the bottom. Top number minus bottom number, which is 24 minus 12, which is 12. The protons is the bottom number, which is 12. The electrons is the bottom number and depending on the charge. Okay, so obviously the electrons is 12, used to be 12, then 2 electrons were removed to become 2 plus, so now it's 10. So we have the neutrons and the protons are equal to each other, so this is not a solution. Let's see here, potassium, and the number of neutrons of potassium is 39 minus 19, which is 20. 39 minus 19 to get the number of neutrons. The protons is 19, as we said, protons is the bottom, and electrons is 19, and then 1 electron was removed, so it's how much? 18. Okay, so this is what we want. We want the number of neutrons different than the number of protons, different than the number of electrons. Here the number of neutrons is how much? 7, because 14 minus 7. Then the number of protons is how much? Also 7. So immediately you can stop, because the neutrons and the protons are 7, and this contradicts our statement. Moving on. This is not a solution. Sulfur. The sulfur in neutrons is how much? 32 minus 16, which is 16. And the protons is how much? 16 as well. So you can stop. It contradicts our statement. Okay? I'll give you guys a minute. Deduce the number of subatomic particles. Okay. The mass number is always the number at the top. Atomic number is always the number at the bottom. Number of protons is the number at the bottom always. Number of electrons is the number at the bottom, but it also depends on the charge. I'll explain now. The number of neutrons is the top minus the bottom. Okay, what do I mean by number of electrons depend on the charge? So here is 56 and there's no charge, so it remains 56. Aluminum 13 remains. But here for bromine or bromide ion, it's originally 35 electrons, but an electron was added, making the total charge negative. So it's 35, and then you add one more electron, making it 36. Fe, there was 26 electrons, 2 were removed, making the total 2 plus. So now it's 24 electrons. The number of electrons are 24. Moving on. This is easy. Atomic symbol for titanium is 4822 titanium. Which of the following statements about titanium is true? The atomic number is 48, wrong. Atomic number is 22. Number of neutrons 26, yes. We said to get the number of neutrons you do 48 minus 22, which is 26. The mass number is 22, wrong. Mass number is 48. Mass number at the top, atomic number at the bottom. Mass number top, atomic number bottom. Mass top, atomic bottom. Number of electrons 48, wrong. Number of electrons is 22. Number of protons 26, wrong. Number of protons is 22. Moving on. Copper has a transition metal that has 29 protons and 35 neutrons. So how do you construct the atomic symbol? Obviously you put the protons at the bottom, 29. So I can immediately neglect this. I can neglect this. Then 35 neutrons and 29 protons make up the mass number. So 29 plus 35 is 64, which is the mass number. You put the mass number at the top. Mass number top, atomic number bottom. So this is the correct answer. Moving on. What is the maximum number of orbitals that can be found in the third energy shell? So let's see here. The maximum number of orbitals that can be found in the third any shell per shell is n squared. So if you want the third energy shell, what do? You do 3 squared, which is 9. Next, the surface of a metal is struck by electromagnetic radiation of increasing energy. Electrons are observed, whatever. For the energy of the photons is 4.19 times 10 to the minus 19 joules. What is the wavelength? Okay. So obviously, here I have formulas. This V represents the frequency in hertz. This C represents speed of light in vacuum. And then this is the wavelength. And then the energy of one photon is equal to Planck's constant times the V, which is frequency. Let's write them down. So the energy equals hv, and V equals C over lambda. Nice. What do I have? What do I need? I need the wavelength. Nice. What do I have? I have Planck's constant. Okay. I have the energy. And I have the speed of light in vacuum. But I don't have the V. So I need to make a relation for V in both equations so I can substitute V directly. So what do? I can say for the first equation that E over H equals this nice V, right? Then I substitute it into this equation, saying E over H equals C over lambda. Cross multiply, I'm trying to find lambda. 4.19 times 10 to the minus 19 lambda equals, I'm gonna write down, I don't know what space, 3 times 10 to the power of 8 times 6.63 times 10 to the minus 34. Let's see where this gets us. So obviously I solved it before. Plugging on the calculator, you get 4.74 times 10 to the minus 7 meters. Okay, but to get it in nanometers, you should get 10 times 10 to the power of minus 9. How do I get minus 9? I move it 2 decimal places forward. So I get 475 nanometers. Okay. Then, obviously for each color there is a certain wavelength. Based on the table, choose the color of light that caused the electrons to be ejected from the surface of metal. From the surface of metal, we need 475, the number 475 nanometers. 647 starting, no. 500 starting, no. 575 starting, no. 491 too big. 424 maybe. From 424 until 491, we fall in this range, which is the blue color. Okay. Next. Here, very important topic. Free electron in the box representation. Let's start here. We just fill out these. Okay, so what I'm drawing here is something called the electron in box representation. It essentially shows you the orbitals and how many electrons are fit in them. And now I'll explain it more in depth. Let me just finish this. Okay, so for the s orbital, it's one box, okay, containing only a maximum of 2 electrons. Then for the p orbital, it contains a maximum of 6 electrons. D orbital contains a maximum of 10 electrons. F orbital contains a maximum of 14 electrons. This you have to memorize it. Okay. To understand it more, the S contains only a box. P 3 box. D 5. F 7. If you notice a pattern, 1, 3, 5, 7, odd numbers. Then you fill in one arrow up, one arrow down, and then arrow up, arrow down, up, 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 down, whatever, and you keep the cycle going. Okay, when you do up, down, you get 2 electrons. Up, down, up, down, up, down. So 2 times 3, 6. Up, down, whatever, times 5, 10. Up, down, times 7, 14. So this is where it came from. These boxes are suborbitals, in fact. Okay. Let's see here. Nitrogen. Nitrogen has 7 electrons. First, let's write the electron configuration. 1s2, 2s2, 2p6. Oh no, not 2p6. Sorry. 2p3. Okay. So what do I have? Let me draw it. So obviously, in S, it's only a box, we said. So 2 electrons, so 1, 2. Then 2s2, another box. 2p3. For the P and for anything other than S, the boxes must be stuck to each other, as I did here. So for the P, 1, 2, 3. Okay? Then there's 3 electrons. Always, in this case, you have to fill up, then down, then up. You can't like do 1, 2, 3, and then you no. You have to fill first up, down, then up, down. You know, like so up, down, up, down, up, down. That's a sequence. You always fill one box first. Okay. Reading the question: what is the correct electron in the box representation that has the lowest energy? To have the lowest energy, becoming more stable, it needs to lose this electron, and this electron goes here. Why? Because more subshells are occupied. So it will look something like this. This is what we call a free radical. So option A is the correct option, as we drew here. You can immediately also omit, because here there is no 2s2, so this is wrong. Here, you cannot leave the first box empty. This is completely wrong. Here, I don't know where they got the 3s2. Wrong. And yeah, so it's wrong. Okay? And as I told you, we call this classification a free radical. Moving on. Identify a free radical element. How to identify a free radical element? You do the electron configuration, then you draw the boxes. So for fluoride, nothing. It's 1s2, 2s2, and then 2p, how much? 2p5. Then you draw whatever the box, then box. Okay, 1, 2. 1, 2. So these are 4, and then I need one more. Oh, free radical. So because why? There's a lonely pair of electrons occupied by the subshell, so I call it a free radical. You can try for the rest. You're gonna get that all shells are occupied. Okay. Moving on. Which of the following have a half-filled subshell upon losing 1 electron? The magnesium is 1s2. Originally 1s2, 2s2, 2p6, 3s2. Nice. The rule is when an electron is lost, it's taken from the highest coefficient always. Why? Because this is the valence electrons. It's the outermost. So it's on the outermost shell. So if it's gonna lose one electron, this is gonna become 3s1, and the rest remains the same. Drawing it 1s2, 2s2, and to imagine the whatever they are. So I'm not gonna draw it every time. And the 2p6, full arrows. Then the 3s1, up, only one arrow. Where's the second arrow? No, we only have one arrow because it lost an electron. So here, as you can see, it's half filled. Sorry. Okay. Okay. That's for the magnesium. If you try for the other ones, here for sodium becomes Na10. Do the electron configuration of Na10. Na7 becomes Na6, and Cl. Remember, Cl is if it gains one electron, it becomes Cl minus. Okay, so originally اصلا Cl minus, so it becomes 18 electrons. You have to be careful on that one. Or no, sorry, what am I saying? No, this is wrong. If it loses one electron, it becomes 16. Sorry, so Cl 16. My bad. But you get the same representation and everything. Okay, sorry, I had something. Moving on. Which of the following are true about 2px and 2py? Okay, now we go to the degenerate orbitals. What are degenerate orbitals like? As we say بالعامية, like quickly. If you see the same orbital, like let's say px and py, if you see p and p, okay, and it's the same coefficient, which is 2, it's degenerate. Why? Because, okay, but like in a proper way to say it, they have the same orbitals, okay, and the same coefficient means the same energy shell. So for it to be degenerate, لازم same coefficient, which is energy shell, and it must also be what? Same orbital. Okay, they are at the same energy, but in different sublevel. Wrong. The same sublevel. Hydrized orbitals? No, it's not hydrized. Hydrized يعني with water. شو دخل? They occupy the same subshell but in different energy level? No. Okay. I'll give you guys a minute. Moving on. What is the correct electron in the box representation that has the lowest energy for oxygen atom? This question is in the course revision. Critical. Expected to be in the exam tomorrow. So oxygen, what is oxygen? What is 1s2? 2s2, these are 4, and 2p, how much? 4. Drawing the boxes. So obviously up, down, up, down, and then up, down, up. We see empty. And I told you, lowest energy always, you need to take one of these electrons. Place them here. So as you can see here, they took the electron that was here and they placed it where? Here. And you can neglect immediately. There is no 3s2. Wrong. Here, they kept this empty. Wrong. No 3s2. Wrong. Here, where is the 2s2? Wrong. So you can immediately say the answer is how much? The answer is what? Sorry, A. Critical question. Please know and understand it. For the orbital shapes, really you have to memorize. I can't really say anything other than that. You have to here memorize it. This is the s orbital, d orbital, and p orbital. And for A-level students and AP students, I guess, yeah, good luck if you're doing the A-level and the AP. But for us also, we have to memorize it. For the A-level students and AP students, I believe you have to memorize all of this and more. So I try guarding as much as possible. So if you're doing A-level, really good luck. Sodium loses one electron when reacting with chlorine to become NaCl. What is the shape of the orbital that from which the electron is lost? We go to the periodic table of elements. That's step 1. Na has how much? 11 electrons. Okay. What is the shape of the orbital from which an electron is lost? Okay, so what do we do? 1s2, 2s2. We said 11. So, wait, what? Oh, yeah. We said 11, so. La, we said 10. So 2p6, sorry. 2p what? p6. This is the electronic electronic configuration. But why would it be S? Wait a second. Okay, so sorry. So I did the mistake again of bad math. So Na we said is 11 electrons. So Na 11. It is 1s2, 2s2, 3p6, and sorry 2p6 and 3s1. So which orbital is removed? The s1 because it's at the highest energy. So the s orbital is removed, and if you see, that's the s orbital. Moving on. Below is the complete photoelectron spectrum of pure element X. What is the electronic configuration of element X? Okay. How do we do it? The first one is obviously here is the highest. Here is the highest energy, here is the lowest. As you go here, you're decreasing the energy. Okay? Okay. Starting here is the hardest one. Why? This is the 1s2. 1s2 is the hardest to remove. Why? Because it requires the most energy because it's nearest to the electron, to the nucleus, sorry. So it has the highest attraction to what? To the nucleus. Okay? So obviously this is 1s, and the relative number of electrons, as you can see here, it moved 1, 2. So there's 1s, how much? 2. Then, following it is 2s2. Okay, so this is a 2s, and how much does it have? 2. Its peak reaches 2, as you can see here. Then, we know it's 2p something. Let's see, 1, 2, 3, 4, 5, 6, 2p6. Then 3s, 2. Then 3p1. Then you choose the option. Easy, easy. There's questions in the course revision. Expect to see it tomorrow. What is the element? Obviously we had here how much? We had 10 electrons and 3. So you see 13 atomic number. Where's the atomic number 13? Aluminum. That's your what? That is your element. Element Y to the right of element X. Element Y is, yes, therefore its 1s electron will have a higher binding energy. As you go across a group, the binding energy increases. I just memorize it, I guess. That's the only way I can tell you, really. Memorize it. Okay, consider whatever. Choose the letter, the present speak. Okay. Identify the element. Identify the element. Sorry. Here it's 2 peaks at the 1s2. So 1s2. Then 2s is as well 2 peaks. So 2s2. Then it is 2p. How much? 1, 2, 3, 4, 5, 6. So 2p6. Then 3s2. So either 10, 12, so we look at the atomic number 12, which is magnesium on the periodic table here. Then the outermost orbital is the one here at the outermost right of the photoelectron spectrum. At the photoelectron spectrum, the orbital that is subjected to the strongest nuclear attraction, as I explained before, is A. Because it's nearest to the nucleus. Okay. Moving on. Again, we need to use our formulas. Calculate the energy of a photon whose frequency is 6.11 times 10 to the 14 hertz. Planck's constant is whatever. Speed of light is whatever. Same formula. Immediately, I can think. What do they want? They want calculate the energy. So they want E. E is nothing but hv. I have Planck's constant, which is 6.606. times 10 to the minus 34 times LV, which is the frequency, 6.11 times 10 to the 14. Let's check our answers. Calculator please. 6.626 times 10 to the minus 34 times 6.11 times 10 to the 14. We should get 4.05 times 10 to the minus 19 joules to 3 single bit figures. Okay, moving on. Well, write the electronic configuration of vanadium 2 plus using the SPDF orbital configuration. They give you that vanadium at vanadium being neutral is 23. The atomic number is 23. When it loses 2 electrons, let's first write its normal electronic configuration: 1s2, 2s2, 2p6, 3s2. How much is that? That's 10, and then 3p6, and then 4s2, and then how much? No, this is all 20, right? 20, and then 3d, how much? 3d, 3. Now comes the tricky part. I need to remove 2 electrons. You would think I would remove from here, but no. You always check which number the coefficient is higher and you remove how much its power. And if you remove its power fully, we need to remove more, you remove from the highest coefficient. Then the next highest coefficient, which is 3d. Obviously you need to go with the order S, P, D, F. That's the order. Then the numbers. So 4. So first you check the numbers, you remove fully the numbers. Then if you need to remove more, you check the next highest number, and you compare with the highest sub-energy shell, which is D here. So if we needed to remove more than 2 electrons, we would remove from the 3d3, but we don't. So you just remove from the 4s2, and you write it the same: 1s2, 2s2, 2p6, 3s2, 3p6, and we remove the 4s2, 3d3 remains. It's simple. It's simple. Trust me. Just practice it. Choose the number of isotopes. You see 2 peaks, so 2 isotopes. How to solve the average atomic mass? Easy. You multiply the number at the bottom, the 35, by the percentage, plus the 37 at the bottom into 25 over 100. You will get 35.5. You will get 35.5, inshallah. Okay, which is what? Which is chlorine. Let's go here. Where chlorine? 35.5. 35.45 and 35.5. 35.5. Okay. Moving on. Question 20. I hope the internet will SDP today. Okay, we're back. SDP is back. Yalla. Naturally occurring boron is composed of 2 isotopes, 10B, 11B. Average atomic mass of boron is 10.81 AMU. طيب, need to find the percentage abundance. How do you do it? Let's say L10B has X, and then if the total, let's assume the total of them is how much? Is 100. So if 10 is X, 11 is 100 minus X. So again, we do the same step. So 10X plus 11 into 100 minus X over 100 equals, they already give you it, 10.81. 10.81. Let's do it on a calculator. Let's just plug it in, let the calculator solve. So we have 10x 10x plus 11 into 100 minus x over 100 by 100, you get sorry, you get 10.81. Let's check how much the x values are. So the x value is 19. So that for the 10 is 19. For the 11 it's 100 minus 19, which is how much? 100 minus answer 81. Simple. Okay, so the x equals 19. So the 100 minus x equals 81. Simple. Okay. These are basic questions, done them many years before. You guys should know them. This quickly. Relative charge of the nucleus. You should know that in the nucleus there only exists protons and electrons. There only exists protons and neutrons in the nucleus. So if protons and neutrons are only existent, that means that it's only positive. Meaning, if the atomic number is 90, then the charge of the nucleus is plus 90. Easy. يعني come on. أعطاك الatomic number, أعطاك mass number. All you have to do is just plug in atomic number at the bottom, mass number at the top. Atomic number at the bottom, mass number at the top. I keep saying it. Mass number top, atomic number bottom. Memorize it, please. Or else don't go tomorrow. يعني. Don't do the exam tomorrow. It's lagging again. I'll wait for it I'll wait for the question to pop up and I'll resume recording. Okay, bromine radicals ATBR are produced by homolytic fission of bromine gas in the presence of light. Come on, go to the periodic table. Bromine, where's bromine? Group 7, 35 atomic number. Hello. So 35 protons, 35 electrons. Then it's 80, 35. 80 minus 35 is how much? 45 to get the number of neutrons. Easy. Very, very easy, these questions. It should not take you 2 minutes in the exam. Haram. This common sense. You have a positive plate at the top, negative plate at the bottom. You have 3 particles. One that goes towards the positive, one that does not deviate, does not shift upward or downward towards any of the plates, towards any of the charged plates, and a particle that deviates towards the negative plate. Obviously, the beam that deviates away from the positive plate is the protons. Why? Because positive and positive, repels, and protons is positive. The beam that deviates away from the negative is the electrons, because electrons is negative, negative and negative repel. With the beam that does not deviate at all, that keeps going straight, is the neutrons, because it's not charged, so it just keeps going straight. This might come as well. It's in the CQD. Know it well. يا رب يعني يا رب يعني والله. This is memorized. I can't really do anything other than really explaining the proton, neutron, and electron. Proton is +1, neutron is 0, electron is -1, and memorize the masses. I'll give you a minute. Moving on. Memorize again. I can't really do anything. You need to have these memorized. Yeah. And I gave you them here. Okay. Moving on again. Without looking. Yeah, Bohr is an experiment, whatever. Boring scientist, Bohr. Calculate the maximum number of electrons. We said equation بتاعتنا. Maximum number of electrons is 2n squared. There's a difference. Orbitals per shell was n squared. Electrons per shell is 2n squared. So on the fourth energy shell, so what do we put inside of the n? 4. So 2 into 4 squared, which is 2 into 16, and is equal to how much? 32 electrons. Sorry, excuse me, guys. Number 28. I'll pause, and when it comes back, I'll resume recording. Okay, choose a subshell that can accommodate maximum of 10 electrons. Everything is here. D10. Memorize it, please. Please. Next. Wait, is my like when my mic is not working? Okay, mic working, mic. Okay, okay. لا لا يا رب. Really nice question. Consider MGX where element X is in period 4. Write the electronic configuration of X. Okay. Period 4. Let's go. Let's check. But first, you need to have شوية logic of it. Mg is Mg2 plus. And the X we don't know. It's some charge. But here, if you look here, MGX. I guess everyone now knows the crisscross what method. And we know that if here is the same number as here, then the crisscross, yeah, it just remains the same, MGX. So if it's MGX here, then that means the charge here is 2 minus. Common logic, common. This is easy, you should know this. So I need to go period 4, and I go across here. Here is -1, here is -2. Selenium. Selenium is your X. Selenium is your X. But remember, we need to make it 2 minus. You need to remove 2 electrons. Let's write the configuration. First, let's write the configuration. So it's 34. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. How much did it reach? 20, and then 3d10. And then what comes after it? I actually don't know. Let me check. So let's check together. Oh, ya Rabbi. Here. So what comes after the 3d10? ال 4p3. ال 4p what? ال 4p3. 4p4. My bad. 4p4. Because this is all 30. I need 4 more to make it 34. Then this selenium loses 2 electrons. Remember, I need to make it 2 minus, becoming 32. And remember our rule: you look at the highest number, 4 or 4. Then you look at the tertib S PDF, F of P, PDF, PDF S. So S PDF. What's higher, P or S? P. So you remove from the P how much? 2 electrons, making it 32. So it's the same electronic configuration. And 4p how much? 2. That's it. Easy. Okay, so what did I do first? Mg2 plus. Okay. And I have an X. I don't know the charge. Then I see from the compound that's MgX with no subscripts. So the crisscross cancel each other. Okay? That means that the charge must be 2. They told me it's in period 4. I go to my periodic table. Period 1, period 2, period 3, period 4. I go across. Here is charge -1, charge -2. So your element is selenium. So X is selenium. The atomic number of selenium is 34. Lose it, and then I wrote the electronic configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. This is all in total 34. You can check by yourself. Then it loses 2 electrons, becoming how much? 32, right? So I need to remove 2 electrons from the highest coefficient, and of these highest coefficients, the higher orbital in energy, which is P. Okay. Um, Moving on. Bismillah. Select the correct level energy of aluminum. Okay. Easy. It's basically the box, but like in a confiscated or in a complicated way. You know, whatever you want to say. Aluminum is how much? 1s2, 2s2, 2p6, 3s2, and 3p1. Just easy. 1 s2, there's 2 electrons because s2. 2p, 2s2, sorry, 2 electrons, so up down. 2p, as you remember, p has how much? 3 boxes. So here instead of the boxes, just put what? These dashes, and this is called the energy level diagram. Obviously the p6 is gonna be how much? Up down, up down, up down. It's fully filled. So up down, up down, up down, as you see. And then the 3s2, it's a box, up down, as you can see. And then the 3p1, 3p1. Allah. 3p1. Okay. 3p1 هيو 3p1 بس that's it. Easy, simple, خفيف. That's it, that's the question. بس. Okay, write the shorthand electronic configuration. What does the shorthand electronic configuration mean? You bring the noble gas from the previous period and you add to it how many electrons you need. بمعنى in such meaning. What do I mean by that? Fe is 26 electrons, right? 26. Let me find Fe on the periodic table here. I go up the period before it and I check what's the nearest sloping gas. 18. 18. حلو. أنا what do I do? Okay. How do we write this أصلا? Where does it come from? Let me write the Fe normally. So the Fe is 1s2, 2s2, 2p6. Yeah, excuse me, guys. I just sorry. 2s2, 2p6. We said, yeah. 3s2, 3p6, 4s2, and how much do we have left? 4s2 and then 3d. How much? 6. Nice. The argon, the right shorthand configuration. You look at the noble gas before it. We know it's argon. Argon is 18. So let's see. Let me go to 18 and stop. Okay. So 2, 4, 10, and then 2 and 6 is 8. So 10 and 8 are how much? 18. So I go until here. This is all argon. And I write what's remain. That's it. Again, Fe has 26 electrons. I go back to the periodic table. Fe, 26. I go to the period above it. What's the noble gas? 18. Argon. Argon has 18 electrons. I write the normal 26 electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Then I know argon is 18 electrons. I count 2, 4, 10, 12, 18. So I remove all this, put instead of it argon, and 4s2, 3d6. Simple. Very, very simple. Moving on. Okay, here what do we have? Write the shorthand electronic configuration of the following lines. Let me actually not erase. Let me not erase. And it's gonna probably be issue beneficial. Type. Here I have 22 titanium. It lost how much? It lost 2 electrons. Let's first write it as 22. At 22, that's gonna be here. That's the difference. 3d2. It lost 2 electrons. Remember, we say it removes from the highest coefficient, highest number. So this will be removed. Then, obviously, we know it's gonna be 18. اللي هي argon. And the 3d2. So it's gonna be argon 3d2. That's it. Okay. Then, phosphorus. If I write it, 1s2 It's 15. So 1s2, 2s2, 2p6, 3s2. This is how much? 12, and then 3p3. Help. Then what happens? It gains 3 more electrons, becoming this one how much? The same thing, and 3p6. Okay. Help. Let's see. Let's see where phosphorus is. Phosphorus should be somewhere here. You go up, and then the nearest noble gas. Noble gas is neon, 10. You count the 10, which are here, which are where? This. You remove it, you put neon, and you put 3s2 and your 3p6, and your problem is solved. Okay guys, easy question, easy. Just practice it, understand it most importantly. It's easy, nothing difficult. If you have any question, you can always ask. Oh yeah, just solve this. I'll let you guys on this. If you have any question, ask me. Here is where we come. No, here's still, we're still just writing an electronic configuration. Obviously, you need to know it. It's easy, simple. I told you how to do it. Simple. Last question, I think, is the one where there's exceptions. Wasn't there a question with exceptions? Hold on, let me check. Zinc, cobalt, no. في chromium وcopper ولا I remember there was chromium and copper. I guess I'm mistaken. طيب. No problem. Last question. We did 34. Oh, 34, yeah, you guys can do it. It's easy, simple. Just follow this table. As I told you. S1, hold up. Okay. As I said, S you write it and you skip a line. P you write it, skip a line. D write it, skip a line, write the D. Skip a line, write the F. And obviously go with the diagonals. Okay. Last question. Let's wrap it up. Removing a 1s electron from oxygen that requires removing a 1s electron from an oxygen atom requires more energy than removing one nitrogen from a one nitrogen atom because oxygen has a higher nuclear charge. What does it mean? I guess this one just really memorized because oxygen, a nuclear charge, what's the nuclear charge? 2 minus. Nitrogen is going to be 3 minus, which is higher oxygen. It's nuclear charge, so it requires more energy. That's all I can say really. Thank you very much, everyone. Hope you all have a good day. Just for tomorrow, practice well. Remember your rules. It's not a lot of rules. Just if you want, go over the quiz again. I know it's a long video. Go over the quiz anytime you want. And yeah, man, just good luck. Remember your formulas. Remember all the subshells. I hope you all have a great day. Good evening, and just yeah. Thank you everyone for watching. Good luck for tomorrow. If you have any questions at all, obviously feel free to text me or send on WhatsApp, or if you send on the Savage Grade 11 group, I'm sure you'll find as much help as possible. Thank you everyone. Good. See you all later.